Physics 30s, it's T again. All right. Looking on page 117. Okay, Bohr's explanation of the hydrogen spectra, so the hydrogen emission spectrum. Why does excited low-pressure hydrogen gas emit only certain frequencies of EMR? So you can see what you have here in the little display, you have in the visual. You have a high voltage source, and then you have light from excited hydrogen atoms, electrons exciting those atoms, passing through a prism, and you have this emission spectrum shown here. You have infrared, some in UV, and in the visible spectrum you have red, green, blue, and violet emission lines at specific wavelengths. It says first, the high voltage creates current within the cathode ray tube. The electrons collide with the hydrogen atoms and excite them to higher energy levels. Since the excited energies level are unstable, the atoms will drop to lower energy levels. When they drop levels, they lose energy and emit photons. Bohr was able to show that each bright line in the emission spectrum is a unique energy drop. And so you can see for the visual one, the lower level is 2 all of the time. So a transition from n equals 3 to 2 gives red light, 4 to 2 green, 5 to 2 blue, and 6 to 2 violet. And you can see the diagram over here showing the specific energies of those levels, and then these emission lines coming down, okay? So notice 3 to 2 is a vertical line, an arrow going down with R, and then of course 4 to 2 green, 5 to 2 blue, and 6 to 2 violet. Notice the transitions, of course, to the first energy level, n equals 1, are in the UV spectrum, and ones that are transitions to 3, okay, or higher are all in the infrared spectrum. Now it has a little note here about the absorption spectrum. Bohr was able to explain why a gas absorbs the same frequencies of EMR that it emits. To illustrate, Bohr knew that when a hydrogen atom drops from n equals 4 to n equals 2, it emits a green photon with an energy of 2.56 eV, a wavelength of 486.1 nanometers. Clearly, in order to raise the hydrogen atom from n equals 2 to n equals 4, it requires the same amount of energy, 2.56 electron volts. The only photon capable of providing this exact energy is the same green photon. The same reasoning applies to every other wavelength emitted and absorbed by hydrogen. Okay, in evaluating Bohr's model, it could not explain emission and absorption spectra for hydrogen and any other one-electron atoms. Okay, it could not explain the spectra for more complex atoms with more than one electron. Why only certain orbits were allowed? Why the orbiting electrons did not emit electromagnetic radiation as predicted by Maxwell. An accelerating charge should produce EMR and lose energy. And why some spectral lines were brighter than others, and how you can actually split the spectral lines with a magnetic field. It's called fine structure. All right, we'll do some questions on the next page.